crystal structure of semiconductors. Welcome to D Creations Resources. So now if you think of the elemental semiconductor, namely silicon, let us try to understand its crystal structure. So it has diamond lattice, and a diamond lattice can be derived from two face-centered cubic unit cells. So basically if you have two FCC unit cells, where you can say that at the same origin, if you keep one at its place and then the second one you displace it by 1 by 4 in each of the three directions, namely x, y and z. Now the atoms that are within the volume of the original FCC lattice will be forming silicon unit cells. So after the displacement of the second FCC unit cell, only 4 of its atoms will be in the volume. Now if the dimension is A, obviously the volume is cube of that is A cube. So others will move out of the volume due to 1 by 4 displacement along the 3 axes. Atoms in silicon unit cell will be alike, but the structure basically is that of a diamond unit lattice. Now let us consider the case of compound semiconductors. For example, consider gallium arsenide. So it's a 3,5 compound semiconductor as it's known, and the unit cell will be similar to that of elemental semiconductor like silicon, but now there are two different elements. So the positions of atoms which were occupied by only silicon atoms in case of silicon lattice will now be occupied by two different elements. So if, for example, if gallium, out of gallium arsenide, if gallium takes the position of atoms of a non-displaced FCC unit cell, and then arsenic will take the position of displaced atoms. So together they will constitute the unit cell of gallium arsenide, and in fact it's a zinc blende lattice. So CDT also has same zinc blende lattice, though it's a 2,6 binary compound. Now you might wonder this, what is the situation for 3,5 compound, or what about the semiconductors which are, say, tertiary or quaternary, etc. Now let us talk about unit cell of compound semiconductors. So consider gallium arsenide. It's a binary compound semiconductor, 3,5 binary. Now the unit cell will be similar to that of elemental semiconductor, that is silicon, but now there are two elements here. So all the positions were earlier occupied by silicon atoms only when it was silicon lattice. Now here some of these positions will be occupied by gallium and some by arsenic. For example, gallium can take the position of atoms of a non-displaced FCC unit cell, and then arsenic will take the positions of displaced atoms of displaced atoms. So that FCC unit cell. So together it will be gallium arsenide. Now this arrangement is basically the zinc blende lattice. So all these 3,5 compound semiconductors, or even 2,6 binary compound semiconductor like CDT also has zinc blende lattice. Now sometimes in order to have ternary or quaternary compound semiconductors, the elements which are occupying these positions can be replaced by a mixture of other elements. For example, consider that gallium atoms can be replaced by a mixture of aluminium and gallium, so that together there will be a formation of a ternary compound, aluminium gallium arsenide, AlGaAs. Now aluminum can replace gallium in any amount, right from 0% to 100%. And of course, if aluminium had replaced gallium completely, then it would have been aluminium AS, so AlAs binary compound. But for the situation where it's not replacing it completely, we will write it as AlX Ga1 minus X As. So X can vary from 0 to 1. For example, it could be Al 0.4, Ga 0.6, As. So aluminium, gallium, arsenide. Now if both gallium and arsenic are replaced by other atoms, then it can even go to a quaternary compound. So let us imagine that, like previous case, gallium is replaced by a mixture of aluminium and gallium, and arsenic is replaced by a mixture of arsenic and phosphorus. So in that situation, we will have the compound as AlX Ga1 minus X AsY P1 minus Y. So it could be like, for example, Al 0.6, Ga 0.4, As 0.3, P 0.7. That could be one of the combinations. And here the advantage is, by controlling this factor of X, you can even control the properties. So you are able to even vary the band gap using particular design of these semiconductors. So that is the advantage in this situation.